Okay, on to the calculus of polar. Now, in polar form, there's only a couple of things that we're going to do. The first is that we're going to deal with area. Okay. Now, I'm going to show you how area is a little bit different in polar form before we move on. Okay. Now, whereas in rectangular form, if we wanted the area under a curve, and we've talked about this 1,000 different times, we get these rectangular cross sections, right? And we add them up. Basically, we get an infinite number of infinitely thin rectangular cross sections. And so basically what we're really doing is we're just going from A to B, and this is height, right, times width. And the width, of course, is my dx, and the height is my, the function value, right? But you got to remember that polar goes around, okay? And so we're not dealing with a triangle, we're dealing with something like this, okay? And that is not so much a rectangle as it is the sector of a circle, okay? Now the sector of a circle is a fraction of the area, right? So it's pi r squared times some fraction. Well, the fraction is a fraction of 360, but we don't want to deal with degrees, we want to deal with radians, so it's a fraction of 2 pi. So it's whatever your theta is, 2 pi, right? And so that would be the area of the sector. Well, notice that right there. Boom, boom. So all of a sudden, that goes away, and what I get is I get 1/2 r squared theta, and that's the area of a sector. But that's static geometry area of a sector. I'm trying to figure out how to represent an infinite number of circular sector cross sections, right? And so what happens here is when I apply this to an integral, I get 1/2 r of theta squared, and that theta becomes my d theta, and that's why the area in polar form looks like that, because it's related to the area of a sector. Because we're not going height times width, we're going 1/2 r squared theta. Okay, so the theta becomes my d theta, the r becomes my function r, and of course the 1/2 is just a constant and it gets plopped down in front. Okay, so that's kind of nice. Let's go ahead and actually deal with an example. What do you say? Okay, and I have a couple of printouts here that I've made, and we're going to go ahead and use those. And if I feel like I need different ones, then I'll sort of figure that out between now and the time that I start the second video. Okay, so this is r is equal to cosine 2 theta. Okay, let's say that I want to find the area of one petal. Okay, I want to find the area of one petal. Well, the first thing that I need to do is I need to figure out what the limits of integration are. Okay, but even more so, here's the thing. I can use symmetry to my advantage, and I actually don't need to get the area of the whole thing. I can just get the area of that top half, right, and multiply it by 2. That's going to be a whole lot easier for the sake of my limits of integration. Because here's the thing. I have 4 petals over the span of 0 to 2 pi. That means that each petal is formed by a span of pi over 2, right? Because it's just 2 pi divided by 4, okay? But this is 0 to pi over 4 because it's half of that, right? So what we're going to do is we're going to do 2 times the area from 0 to pi over 4. So let's go ahead and go 1/2, okay, and we're going to multiply it by 2. 0 to pi over 4 of cosine 2 theta squared d theta, and that should be it. Now some of these are probably going to require you, and of course those cancel out, some of these are going to require you to do them by hand. So we'll go ahead and do a couple of them by hand, but mostly we're just going to be setting them up, okay? Now, if we harken back to trig integrals, we know that this is going to be one of those ones that is a power reducing, okay? So we wind up 1/2 out in front, 0 to pi over 4, and that's 1 plus cosine of 4 theta d theta, or 1/2 d theta from 0 to pi over 4, plus 1/8 integral from 0 to pi over 4, and the reason why it became 1/8 is I need to include a 4 d theta to do my u substitution over here. That winds up being 1/2 theta from 0 to pi over 4 plus 1/8 sine 4 theta from 0 to pi over 4. Now, plug that into here. I'm going to get pi over 8 minus 0. Pi over 8 minus 0. And this is going to be, when I plug in here, I'm going to get sine of pi. Okay. Sine of pi is 0, so that's 1/8 times 0 minus 1/8, and then sine of 0 is 0, and oh my gosh, it looks like it's pi over 8. Okay, so that winds up being the area of one petal. Okay, well, and it's going to work out a little bit differently if you do it maybe cosine of 3 theta, because remember, cosine of 3 theta has 6 petals, but only 3 of them are visible, okay? And perhaps we'll do that one in the next video. I'll go ahead and make myself a little note. R is equal to sine, let's do sine of 3 theta in the next video, okay? Well, sometimes it is that straightforward, and sometimes it's not, okay? And I'm sure that you knew that that was coming. So we're going to go ahead and we're going to do one that's a little more complicated. Instead of one area, we're going to deal with the area between graphs, okay? And let's say I want the area that is contained inside of both, okay? So I need inside of both. Okay. Here's the thing with dealing with one's area between the curve and polar. Sometimes you're going to have to break it up. The question is how to break it up. And the question is also, when do I legitimately have to use calculus and when don't I? Okay, I hope that's showing up. I think that's dark enough. Here is one of the really cool things. This right here is a cardioid. Okay, it's in the class of curves called limicons. It's a cardioid because this constant right here and the coefficient in front of the trig function are the same. Okay, what I need to realize, however, is this other curve is a circle with a radius of 1, and I don't need calculus to tell me the area of that semicircle. Okay, so really all I need is I need calculus to tell me the area of this portion of the graph that I'm cross-hatching in blue, and then multiply it by 2 because this is symmetric over here. Okay, so I basically need a geometric representation of the area of the semicircle. So I need the area of the semicircle, and then I need to add it to 2 times the area of, we'll call it just the really sophisticated word, hump. Okay? Now, this is going to be really, really easy. Okay, so it's 1/2 pi, and then r is 1 squared. Oh my gosh, that was so difficult. 2 times the area of the hump. Well, I know that it's going to be 1/2. Okay, I know that it's going to be 1 plus cosine theta squared d theta. The only real question that I have is, what are the limits of integration? Well, that should be really, really easy, okay? And the thing is, if you remember drawing these, this, since it's off the screen, I'll write it again, is r is equal to 1 plus cosine theta, right? Now, when is 1 plus cosine theta 0? Okay, well, it's 0 when theta is equal to pi. Because when theta is equal to pi, cosine theta is -1 and canceling that one out. So right here is where theta is equal to pi. Now, when is r going to be 1? Well, it's going to be 1 when cosine theta is equal to what? Well, when cosine theta is equal to 3 pi over 2, or pi over 2. But if this is pi, this is, that's probably 3 pi over 2, okay? Because well, no, actually that's pi over 2. So that's theta is equal to pi over 2, okay? Because at pi over 2, it's 0, okay? And you can, even if you get a little bit mixed up, you can always go and check, okay? You can always go and basically graph it on your calculator, okay? So we'll go ahead and we'll put 1 plus cosine theta. And if you go to the window, you can actually check. You can go, well, let's just graph it from pi over 2 to pi, and we'll see whether I'm right, okay? Now let's go down here and let's actually scale this down a little bit on the x and the y. Delete that. Oh, 1 plus cosine theta. Did I actually get that wrong? Should it be 1 minus cosine theta? Oh, it should be 1 minus cosine theta. Sorry, I botched that up just a little bit. So that actually should be 1 minus cosine theta. And that makes a little more sense. That actually goes from 0 to pi over 2. So we go 0 to pi over 2. And, oh yeah, that is right. Okay, so now we got it straight. Sorry about that. I missed a negative when I was cutting and pasting that into a Word document. So that winds up being minus. And we just confirm with our calculator that that's 0 to pi over 2. Now, I'm not going to actually execute this one because we're actually nearing time to be done with this. But this is going to give you the right answer. You're going to have to FOIL this out, do power reducing for the quadratic term, and it's meticulous and it's detail-oriented and it's burdensome, but it's not overly difficult. And then you just add it to pi over 2, which is how we geometrically got the area of the semicircle. And at that point, you're done, okay? We're going to go ahead, and in the next one, we'll do another area between the curves, along with the 3 petal rows. And then we will move on to finding arc length, and time permitting, we will do a little bit of tangent line action, because finding a tangent line in polar sounds really, really daunting, since the tangent line is in terms of x and y, and you're in r and theta, but actually winds up being relatively straightforward. I mean, again, one of those ones that can at times be burdensome, but not overly conceptually difficult. So you have that to look forward to. Any questions, please do email me. Bye.